ladies and gentlemen. Hello. Welcome to HL Chemistry Flipped Classroom. Today we're going to be talking about drawing Lewis structures. And you're going to need a couple things for this video. You're going to need this page in your workbook. It looks very similar to this. Mine is slightly blown up so you can see the typing a little bit. And you're also going to want to have a periodic table handy. So let's just go ahead and jump right into it. What the top part of the page is doing, it's asking us to do something really simple, which is drawing Lewis dot diagrams for the elements. And we have examples from group 14, 15, 16, 17, so that's right in here in the periodic table. And basically what we're trying to do in this exercise is just find out how many valence electrons that these things have. Finding valence electrons is really simple. We may have talked about it before in class, but just a quick reminder. To figure out how many valence electrons any particular element has, simply count across this direction, skipping this middle part. So this first row has 1 valence electron, this second one has 2, skip all that, 3, 4, 5, 6, 7, and 8. With the exception of helium. Helium only has 2 valence electrons. It only has 2 electrons, period. So you just count straight across. So if we're trying to draw a Lewis dot diagram for carbon, really, the main thing we're discovering here is that it just has 1, 2, 3, 4. Carbon has 4 valence electrons. So the way we write that is we just put 4 dots around carbon, thusly. These each represent an orbital. We don't double up the electrons till we have to, so each sort of side represents an orbital. So as opposed to drawing it like this, I guess, we just sort of distribute the electrons evenly. It's not a huge deal. The main thing is knowing that there's 4 valence electrons. And silicon, given that it's in the same column as carbon, is also going to have 4 valence electrons. It would look like that. Nitrogen is in the 5th column, 1 more over. So again, count over 1, 2, 3, 4, 5. There's nitrogen. It has 5. So we would spread those out, 1, 2, 3, 4. If we have to double up one of them, it doesn't matter where we double it up. We can put it anywhere. Phosphorus, it's in the same column as nitrogen. It would look the same. And so we could keep going. We could keep doing this. Oxygen is right next to nitrogen, so it has 6. 1, 2, 3, 4, 5, 6. Fluorine has 7. I mean, I'm not even going to bother going through all these in detail. As long as we know how to find how many valence electrons each one of these has, we're in good shape. And neon has 8. And you can take a second and fill in those other ones. Helium. How many valence electrons does helium have? Helium only has 2 electrons, period. Both those electrons are in its outer shell, so it has 2. How many electrons does hydrogen want? So what this means is, we've talked in class before how the noble gases, they're the cool kids of the periodic table. All the other elements are trying to imitate them, get a similar electron configuration to them, trying to get 8 electrons in their outer shell. All of the noble gases have 8 electrons in their outer shell, except for helium. Helium only has 2. Now, hydrogen only has 1 electron. It likes to imitate helium, so hydrogen wants 2 electrons. It likes to imitate helium and have 2 electrons. Every other element wants to have 8 electrons in its outer shell. So that's the main take-home message from this beginning part here. We're figuring out how many valence electrons things have, and we're deciding how many valence electrons various elements want. They all want 8, except for hydrogen, which wants 2. 8 being the so-called octet rule. So we're going to try to learn about Lewis structures today, and Lewis structures are just representations of molecules, and it's basically a way of representing a molecule on paper. And there's a series of steps, okay? And we're going to kind of go through some examples and take a look at these steps, but one of the most important and the very first thing you're going to want to do is count up the total valence electrons available from all elements involved in the bond. Add or subtract the necessary amount of electrons that the structure has to charge. And I'll be showing you examples of this shortly. This number is super critical. It's something you should do and be thinking about whenever you make Lewis structures. You're going to guess the central atom, and these are best really seen by example, going to connect elements with lines and so forth. Probably the most important thing here is a Lewis structure must meet two requirements when it's complete if it's correct. It must use exactly the number of valence electrons you calculate in step 1, and each element must have 8 electrons around it, including those they keep and those they share. Hydrogen, as we said, only wants 2, so it's the exception to that. So, like I said, this will make more sense by example. So let's look at a couple. If you flip to the end of this, it asks you to draw Lewis structures for these things. I'm going to do a few of them for you here as examples. So, take fluorine. So step 1 says if you look back at it, count the total number of valence electrons involved from all atoms involved in the bond. Well, there's a fluorine, and if we count, fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. It's right here. It's in the 7th column over. So it has 7 valence electrons, but there's 2 of them. So that means I have a total of 14 valence electrons to work with. So I've done step 1. Got that number. It's super important. Guess the central atom. Well, this step doesn't apply because there's only 2 atoms. To have a central atom, you need at least 3, so we can skip that for now. Sometimes we'll have to do this, most times, but for this one we can skip it. Number 3, connect each element to the central element with one line. This line represents 2 electrons being shared by the elements. These electrons count for both elements' goal of getting 8 valence electrons. That's important to keep in mind. Subtract 2 electrons from the total you counted for each line that you draw. Okay, so here's what I do. I take my fluorine, F. There's no central atoms, so we'll just put them together right there. We're going to connect them with a line. That line represents 2 electrons that are going around both fluorine atoms. So imagine these electrons kind of making loops around both fluorine atoms, and they're going so fast it's kind of like they both have them. So they're sharing them. It's a covalent bond. It's a shared pair of electrons. So since I've used 2 electrons in the making of that bond, that means I have 12 electrons left to go. So we're on step 4. It says determine how many electrons are left over. Add these as dots to elements that still need more electrons. These dots represent kept or unshared electrons. Okay, what I mean by that is, remember, these fluorines are trying to get 8 electrons in their outer shell. So they would like to have 8. Now, right now, each fluorine has 2. Because remember, this counts as 2 for both. So this fluorine would like, quote unquote, like, to have 6 more electrons. And I'm representing those as dots around the fluorine. So since I've used 6 electrons, since I've drawn 6 dots, I can subtract 6. That means I have 6 electrons to go. This fluorine is in good shape. It has 1, 2, 3, 4, 5, 6 electrons it's keeping for itself, and 2 that it's sharing. That's 8. 6 plus 2 is 8. That's what it wants. And hopefully you can see that this fluorine would also like to keep 6 electrons. I've used another 6. 0. So here I have my Lewis structure. And it is finished. And basically, if a Lewis structure is correct, if you've drawn one that works, it's got to meet 2 requirements, like I said. It's got to use exactly the number of electrons counted in step 1. We did that. Each element must have 8 electrons, including those they keep and those they share. So we tabulated the number of electrons. We used exactly 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And each has 8 electrons around it. It has 1, 2, 3, 4, 5, 6 it keeps, and 2 it's sharing. The line counts as 2 for both. When you are evaluating this step right here, if each element has 8 electrons around it, the line counts as 2 for both. Okay, so I'm going to do another couple of examples. These can definitely be confusing at first. We're going to look at H2O. I'm going to quit flipping back and forth to the steps. I'll just kind of reference them for you. So the first thing we need to do is count the total number of valence electrons. Now, oxygen, it's in the 6th column, so it has 6 valence electron. Hydrogen, it's in the 1st column, so it has 1 valence electron, but there's 2 hydrogens. So that's 2. 6 plus 2 is 8. So we've got 8 electrons here to work with. Step 2 says guess the central atom. Now what we mean by this is there's a couple of different ways that we could connect these. For instance, like that would be one way, or like that. Usually there's only one way they would actually work out properly. So when it says guess the central atom, usually is the single element, the one where there's only one of them. This oxygen is probably going to be in the center, and the hydrogens are going to be connected to it. That's what you're going to want to do most of the time. So that's how we're going to start. Now, I have used 1, 2, 3, 4 electrons here because I've made 2 lines. So I'm going to subtract 4 electrons just to keep track, and that means I have 4 electrons left to go. So the next thing we need to do, we've basically done step 3 at this point. So step 4, determine how many electrons are left over, as these are dots to elements that still need more electrons. So the hydrogen has 2 electrons. Remember, we already decided hydrogen wants 2 electrons. So hydrogen's good to go. It's got this bond. Remember, this bond counts as 2 electrons. When we're evaluating this part right here, that line counts as 2 electrons for both. So the hydrogen's good to go. It has its 2. Oxygen, right now, has a total of 1, 2 electrons it's sharing here, 3, 4 electrons it's sharing here. So it would like to have 4 more electrons. And lo and behold, that happens to be exactly what we have. So I'm going to add those as dots. And if we look at step 5, we've met both the requirements. We've used exactly the number of electrons calculated in step 1. We did that. And we've got each element having 8 electrons. Well, the oxygen has 8. Remember, hydrogen, it's an exception. It only wants 2. So this Lewis structure is correct. It's a good representation of the H2O molecule. Let's look at another example. Keep going here. PCl3. So, step 1. Calculate the total number of valence electrons. Phosphorus. Phosphorus is a nitrogen's column. That's the 5th column over. So the phosphorus has 5 valence electrons. Chlorine is in the 7th column. It has 7 valence electrons, but there's 3 of them, so that's 21. So 5 plus 21, we've got 26 total electrons to work with. Okay, so we did step 1. Step 2. Guess the central atom. Usually it is the single element. The molecule contains only 1. Okay, well there's only 1 phosphorus. So that's probably in the center, and all 3 chlorines are probably attached to that phosphorus. That's kind of how you want to usually do it more often than not. Put the single one in the center and attach everything else to that. So I've drawn 3 lines. That's a total of 6 electrons. So that means there's 20 electrons left to go. There's 20 electrons that I have to represent in this picture. So we've done step 3. Step 4, we're determining the electrons left over. There's 20, like we said. Add them to the elements that still need more electrons. Well, let's look at the phosphorus. Phosphorus has 1, 2, 3, 4, 5, 6. It has 6 electrons that it's sharing. So it would like a total of 2 more. So I'm going to go ahead and put those on the phosphorus. Now the phosphorus, and also remember to subtract them here. 18 left over. So the phosphorus has 2 electrons it's keeping for itself. So 1, 2, 3, 4, 5, 6, 7, 8. The phosphorus is good. It has its 8 electrons. Keeping 2, sharing 6, it's good to go. The chlorines only have 2. This chlorine has 2 that it's sharing. It would like 6 more. Now it's going to be good. Keeping 6, sharing 2, that's 8. I've used 6, that's 12. Maybe you can see that all 3 chlorines are going to be just the same here. I can put another 6 electrons there, and another 6 electrons there. That's 12 electrons. So I've met the first requirement. I've used exactly the number of electrons that it says. I have none left over, and also everything has 8 electrons around it. So that is a good Lewis structure. Now, I know what you're thinking, like, geez, Mr. Lewis, on the other videos by now you would have popped in and shown a funny picture or a GIF or a funny cat picture. Well, you know, technology being what it is, the way I'm filming this video, I can't do it. But I did find this little gem. Look at this. Look at this cute little guy. It's like he's on a bike almost. Anyway. Awesome. Okay. Well, we're going to do a couple more examples here that are slightly different. Notice that we haven't got past step 5. There's a couple other wrinkles that can come up, and that's what we're going to take a look at next. One thing we haven't came across yet is this right here: add or subtract the necessary amount of electrons if the structure has a charge. So OH minus, oxygen has 6 electrons, valence electrons. Hydrogen has 1 valence electron. But the entire structure has a -1 charge. So if you think about it, given that a -1 has a -1 charge, that means it must have gained exactly 1 electron. If it was positive, that means it lost electrons, but it gained 1. So we add that together, we get 8 electrons. So oxygen, hydrogen, I've used 2 electrons, that's 6 left to go. The hydrogen has 2 electrons, it's good to go. The oxygen would like to have 6. 1, 2, 3, 4, 5, 6. So it's keeping 6, it's sharing 2. The oxygen has all the electrons it needs. It has 8, so everything's good to go there. The only other thing that we have to remember to add is when a structure has a charge, you need to put brackets around it like that and put the charge. Otherwise you'll get your answers counted wrong without that charge there. So that's what we do with the charge. If it happened to have been -2, we would have added in 2 electrons. If the charge had been +1, we would have subtracted an electron. So, you know, these Lewis structures can be like little puzzles. Sometimes they're easy puzzles, sometimes they're harder puzzles. So, take oxygen, for instance. Oxygen has 6 valence electrons, so we have 12 electrons to work with. So we take our oxygen, connect them, that's 10 electrons left to go. So you might think, well, let's just split them up. Let's put 5 electrons on each. Except that doesn't work, because we've used all 12 electrons. We fulfilled 1 requirement of our Lewis structure, but 1, 2, 3, 4, 5, 6, 7. Each oxygen's keeping 5, sharing 2. That's only 7. So we're not meeting the second part of our Lewis structure, which is we're trying to get 8 electrons around everything. And what we haven't done is there can be double or even triple bonds if necessary to meet these structures. That's basically what step 6 is saying here. So it is possible that electrons would share, or elements would share 2 or even 3 pairs of electrons. By the way, typically you want to do this in pencil. It's great to do Lewis structures in pencil. I'm doing it in pen. So I'm just going to go ahead and redraw it. Instead of having a single bond between here, what I'm going to do is I'm going to utilize, let's say, these 2 electrons and make a second bond between them. So it would look like this. So there's a double bond between those oxygens. And now, notice the number of electrons is the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used 12 electrons. I've used exactly how many I'm supposed to use. But I've met the second part of the Lewis structure requirements. Each oxygen has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. This other oxygen is the same way. 1, 2, 3, 4. Sharing 1, 2, 3, 4. So keeping 4, sharing 4. That's 8. So that's kind of the basics of drawing Lewis structures at this point. And what would be a great idea for you to do would be to look at the rest of these. I drew, a little less than half of them or so, and see if you could make some sense on how to draw those. So why don't you stop the video, draw those, and I'll come back in a second and we can look at what those should look like. Okay, so I have the answers here to the ones that I didn't already draw out of those ones down there in the bottom. The HCl should look like this. You pretty much should have what I have here. If you drew them in a different shape, for right now, I'd be totally okay with it. Like if you had these Fs straight out like that, for instance, or what have you. But the number of dots and lines at this point is kind of what we're looking for, and hopefully you have them just like mine. NH3 should look like this. CH4 should look like that. Definitely, I think the trickiest one on this is the CO2. I'm going to do that one kind of from scratch here in just a second. And then the NH4 plus. Don't forget, because of the plus, you have to subtract one electron from the total, and you should have a bracket with a plus sign on it like that. It's actually incorrect without that. But the CO2, just in case you had some trouble with the CO2, I'm going to sketch that one out for you right now. So carbon has 4 valence electrons, oxygen has 6, but there's 2 of them, so that's 12. 12 plus 4 is 16. Okay, so when we look at CO2, okay, we're going to guess the central atom, it's probably carbon, and we're going to connect the oxygens to that. So I've used up 4 electrons, subtract those, that means I have 12 left to go. So, you could try some things. You could try, let's see, we'll put 6 electrons on each oxygen. Like that. Well, that fulfills one requirement of the Lewis structure. I've used the exact number of electrons, but the problem is the oxygens are good, 1, 2, 3, 4, 5, 6, 7, 8, but the carbon's not. It only has 4 electrons, sharing 2 here, sharing 2 here, that's only 4. So the carbon's not good. So this Lewis structure can't work. It's not a good representation of CO2. So what you have to think about here is you have to think about double and triple bonds. And again, this is work for a pencil Lewis structure normally. I'm just doing it with a pen for visibility. So something I could try, well, I could try something else. For instance, I could move a couple of electrons over. So we'll take these electrons, move them over to the carbon. So again, now I haven't really improved anything. Nothing's better here. The oxygen doesn't have enough electrons. It has 1, 2, 3, 4, 5, 6. The carbon has 6. Only this oxygen's good. So again, this Lewis structure is no good. What I can consider is the possibility of a double bond. So instead of these 2 electrons, let's change those electrons into a bond. So for instance, we have this. Here's either oxygen. So now if you look at what I have so far, I have 1, 2, 3, 4, 5, 6, 7, 8. So the oxygen has 8 electrons. It's good. And what's actually going to have to happen is we're going to have to put another double bond over here. You can eventually realize that's going to look like that. This is really the only way you're going to get this structure to work out, so that it follows both rules. It has exactly 16 electrons and everything gets 8 electrons around it. Because now, like we said, the oxygen keeping 4, sharing 4, both oxygens keeping 4, sharing 4, it's good. The carbon sharing 8, 1, 2, 3, 4, 5, 6, 7, 8. So it takes a bit of playing around. It's a bit of a puzzle that you got to figure out. You got to try it a few different ways, but hopefully you can get there. Now the next step is why I drew these things in the shape that I did, and there definitely is a reason for that, and it's a skill that we need, but that's going to happen in another video or at another time. So thanks for watching, everybody, and we'll catch you next time.